Now let's look at the fifth problem of division 2, which is reach anywhere. So in this problem, we'll be given a simple undirected graph with n vertices and m edges. We have to check whether we can construct a value of k such that every node is having a path which exists from the starting node, that is the node 1, and the path length should be exactly k. So this is what the question is all about. Now let's look at the sample test cases. So in first test case, we have 3 nodes and then 3 edges. So the edges are 1, 2, and then 2, 3, and then 1, 3. So let me just construct them over here. So we'll be having a graph, and the graph has the edges as 1, 2, and then 2, 3, and then 1, 3. All right. So now we have to find a value of k such that every node is having a path from the value 1, that is from the node 1, so that the path length is equals to the given value of k. Now let's try to take the value as 2, that is the k value is 2. Right. So let's try to construct walk lengths of 2. So can we go from 1 to 3 in 2 moves? Yeah. So we can go in this direction. So and it will be having the path length as 2. Now can we go from 1 to 2 in 2 paths? So we can go to 3 in the first place, and we can then move on to 2. And even this path or this walk will be having a length of 2. Now can we go from 1 to again 1 in 2 moves? So first we can go to 2, and then we can move back to 2. I mean move back to 1 in the second move. So we'll be having a path which has 2 as its length, right? So we can construct a walk for all the nodes from the node 1 such that all the paths having a length as 2. Hence we'll be reporting answer as 2 in this case, right? Now let's discuss how to solve this problem. So let's take a random example. So let's say we have nodes 1, 2, 3, 4, and 5, and then we have connections as 1, 2 are connected, and 1 and 3 are connected. Let's say 2 and 3 are again connected, and then there is another edge, or I mean another edge called 4, and there is an edge between 2 and 4, and also this 3 is having another edge with 5. Now let's just calculate the shortest path for each and every node from the given node 1, right? So if you want to calculate the shortest path for 2 from the node 1, then it will be having a length of 1, right? So the value for 2 will be 1. That is, for the node 2 will be having the length as 1. Now for the node 3, you can go to the node 3 in one move. That is in this way. Hence the third node will be having the length as 1. Now for the fourth node, the length will be 2, and same is the case for 5. And then the node 1 will be having the length of 0, right? Now if you see over here, so 4 and 5 are having a distance of 2, and then 2 and 3 are having a distance as 1, and 1 is having a distance of 0. Now let's just try to scale these values up. We are reaching to 2 in one move, right? That is, we are coming from 1 straight away to 2. Now can I increase this number of moves? That is, can I scale this number of moves from 1 to 3 or to 5 or so on? Yes. So we can go back to 1, and then we can come back again, right? So in this case, we are converting the number of moves from 1 to 3, right? Now if you perform the same move, that is going forward and coming back, then we'll be attaining 5 number of moves. So from 1 we went forward and we came back, which gave us 3 number of moves, and from that we again did the same operation, which gave us 5 number of moves. So it's very easy to go from one odd value to another odd value. Now same goes for the case of even. So it will be easy for us to convert some 2 number of moves into 4 number of moves, and so on. So that's what I meant by scaling. So we can scale this value of 1 to any of the odd values, let's say 3 or 5, and we can scale this value of 2 to any of the even values, that is 4, 6, and so on. right? Now, why am I discussing these things? So we want a common k says that all the values are having the same path lengths, right? Now, if they are having the same parity, then I can just easily scale up, right? So if these two guys were having even parity, then I can easily scale these values by just going forward and coming back. So they'll be having the same parity, hence I can easily scale up, and then we'll be arriving at a common k. So we can only arrive at a common k when all are of the same parity. So the answer will only exist if all the path lengths are having the same parity, right? So we can only switch between the same parity elements. That's it. So we have only two parities. It is odd and then even parity. So we'll be constructing the shortest odd length and then shortest even length paths for each and every node. Let's say the target node is 4. So for the fourth node, I'll be constructing both odd length paths and then even length paths. And among them, I'll be taking the shortest length. So the shortest even length will be 2. That is, we can go in this direction. And the shortest odd length for the node 4 will be 3. That is, if we go in the direction of 1 to 3 and then 3 to 2 and then 2 to 4. So if we move in this direction, then we'll be getting the shortest odd length path as 3. So let me just write them over here. So this will be the shortest odd distance and then even distance from the node 1 to each and every node. So if you see, let's take a random case. Let's say the case of 1. So the shortest odd distance for 1 will be 3. So how to construct that? So we can start from here. Let me clear this up. Right. So we can start from here. So we can move from 1 to 2 and then 2 to 3 and then 3 to 1. So we'll be having a walk which is having a length of 3. So 3 is the shortest length, shortest odd length for the value for the node 1. And this value is 3 actually. Because we can go to 4 in 3 number of moves. That is this way. 1 to 3, 3 to 2 and then 2 to 4. Now once we get the shortest values, we'll be just taking the maximum value among all these values. And this should be done separately for both odds and then evens. Right, so this is for evens case and then this is for odds case. And why is that so? Because the largest value among these values can be considered as a k value. As I told you over here, we can scale up the values between the same parity. So I can easily scale up this 1 to 3. And even in this case, if there is a node with 4 as the value, then I can easily scale up these values of 2 and then 0 to 4. So that's why I'll be taking the largest value as the k over here. So let's say this is k2 and then this is k1. Now among these two values, we'll be taking the smallest value. So the final answer will be nothing but it will be the minimum value among the max of odds and then the max of evens. Right. So what we're doing is we are just trying to find out the shortest odd distance and the shortest even distance. So as we can only scale up between the same parity, so we'll be considering these cases separately. And among all these values, we'll be taking the maximum value because that's one of the values to which we can scale up the lesser values. So we'll be taking the maximum of these two odds and the even cases. And then among them, we'll be taking the minimum value, which could be considered as the ultimate value of k. Right. So if this minimum value is not possible, then we'll be printing the answer as -1. So this is how we can solve this problem. Now let's discuss the code for this problem. So at first, I'm taking the input for the number of vertices and then the number of edges. Now for the given graph, we'll be constructing an adjacency list. So I'm just taking the input for the edges and then I'll be pushing v into the adjacency list of u and then u into the adjacency list of v. So now the graph is obtained. So as discussed over here, we have to find out the shortest odd distance and then even distance. So for this, we'll be basically doing a breadth first search, that is BFS call. So with BFS, we can easily find out the shortest distances. That is, we'll be first pushing this particular node and then we'll be going to the next level. So in the next level, actually, I'll be pushing the node and then the parity into the queue. I will be pushing 1, 0, which means that 1 is the node and then the 0 is the parity. That is, it's of even parity. Now as I'm going to the next level, so I'll be changing the parity because whenever we go to the next level, we are moving one number of moves, right? So as 1 is odd, so the parity will be changing. So whenever we are going to the next level, the parity will be becoming 1 and then the number of moves will be 1 plus the parent's value. That's what I have to do, right? So just concentrate from here. I'm declaring a queue which has its elements of the data type pair, and I'm pushing in two values. So the first value is always a node, second value is parity. So I'm pushing in 1 comma 0, which means that 1 is the parent node or the root node, and it's of the parity 0, which is even. Now I'll be doing this particular operation until the queue is empty. So the operation is that I'll be taking the first element, that is queue dot friend, and I'll be passing it. First value among the pair will be having the node, and then second value will be having the parity. Now I'll be going one step below. So I'll be going to the nodes, and then we have to check whether whether this is the first time that I'm visiting that particular node. There'll be two parities, right? So I'll be visiting each and every node for two parities. One is for odd parity, and another one is for even parity. So I'll be constructing a distance vector which is having a dimension as 2 into n, and this 2 is for denoting the parity, that is, it could be taking value of 0 or 1, and this is for n number of nodes. So whenever first value is 0, then it denotes that for the current node I'm looking at the even parity, and if the current first value is 1, then it means that for the current node I'm looking for odd parity. Whenever we move to the next level, it will be having a different parity as that of the roots parity or the parents parity, right? So as the parity is given as parity over here, so as I'm going to the next level, the parity will be changed as 1 minus parity. So if the 1 minus parity of this particular node is not visited, that is -1, then I'll be updating that particular distance. So the distance of this particular node for the parity is 1 minus parity will be 1 plus the distance of its parent, and the parent is nothing but it's the node over here, right? So I'll be just writing it over here. So for a given node, let's say IT, its odd parity will be, so distance of this one, so distance of a node called IT with odd parity will be nothing but it's be 1 plus distance of the node, that is the parent node, with even parity, and same as the vice versa. So the distance of IT, that is for a node with even parity, will be 1 plus the distance of its parent with odd parity. So as I'm adding 1 here, so the parity should be changing, right? So it will be going one step below. That's why they are differing over here. So distance of 1 minus parity of the node IT will be 1 plus the parent's node, but with the opposite parity. And after updating the distance, I'll be pushing that particular node into the queue with its appropriate parity. So once this is done, we'll be processing the result. So how to process the result? So with the BFS call, we'll be arriving at this particular result. That is, we'll be computing the shortest odd distance and the shortest even distances. Right? Actually, I'm initializing all the values of distance to -1. So whenever some distance is -1, it means that that node cannot be visited in the odd number of moves or even number of moves. Now we'll be calculating the answer for odd case and then even case. So it's very easy. So for odd case and even case, we'll be taking the maximum value, and then we'll be minimizing that maximum value. So that's exactly what I'm going to do. So I'll be initializing two loops over here. So the first loop is for checking whether it's odd or even. So whenever I is equals to 0, it will be even, and whenever I is 1, it will be odd, right? So I'll be having next loop, which is a next nested loop, and it will be going from 1 to n. That is, it traverses over all the nodes. Now, if that particular distance is -1, it means that that particular node cannot have a path considered with that particular parity. Hence, I'll be making the distance as infinity so that it doesn't affect the actual answer. So I'll be maximizing this particular current answer. So this current answer will be calculated for both the values of I, which is I equals to 0 and I equals to 1. So I'm maximizing among the parities, and the maximized value will be stored in current answer, and this current answer will be used in minimizing the actual answer, which is this declared over here. Right, now if the answer is equals to int max, that is the infinity value, then I'll be printing the answer as -1, which means that we cannot construct a value of k such that all the nodes are having exactly the same path length as k, right? So in that case, I'll be printing the answer as -1. Otherwise, I'll be printing answer to the console. So this is how we can solve this problem. So first, calculating the shortest odd distance and then even distances for each and every node from the node 1, and we can do that using BFS. And after that, we'll be calculating the maximum answer for odd case and then even case. We'll be taking the minimum answer among those two values. So this is how we can solve this problem.